Alright, good afternoon. Let's continue on the state space model to basically to get a discrete space model from continuous space model. Okay, and then when we finish this part, and then we'll get on to another topic, which is a similarity transformation. Okay, yeah. So this is a continuous state space model. So it's a general space model. So if we want to discretize that into a discrete space model, we discretize it using this zero order Hall equivalent technique. So we're able to basically in the previous lecture to derive and give us a set of state space models, discrete space model. Now this is still this is X at here, okay, yeah, and so with discretize, we'll be able to get this state space equation, and A at here, okay, is equal to e to the power of f capital T. Okay, so T is the sampling time, and B at here, okay, is equal to 0 to T e to the power of f lambda times G and d lambda. So that's the results, okay, of a zero order Hall equivalent discrete state space model from a continuous state space equation. Okay, so we'll look at an example shortly, just to see how we can obtain A and B. Okay, so now the question here basically is, so how to calculate A and B. Okay. So let's look at A first. All right. Yeah. Because if you see the A at here is e to the power EFT, and B has a very similar term, right? It's just e to the power f lambda instead of a capital T at here, right? So it really boils down to basically what does this e to the power of ft equal to? Okay, so if we can find this one here, then we'll be able to find what the B is, right? Okay. Now if you recall. For the continuous state space model, okay, and when we in the previous lecture we derived the solution of this continuous space model, and the solution is x of basically, I'll rewrite it here. Okay, so solution for the continuous state space equation is x of t, okay, equal to e to the power f small t minus t naught x over t naught plus t naught to t e to the power t minus tau times g u tau d tau. Okay, so this is the solution, right? You know, if you have a differential equation and you can solve for differential equation, I mean, this is just a matrix format instead of just scalar values. So here is a solution of that first order differential equation for the continuous one, right? Continuous one. Okay. So let's take a look at this solution in here again. Okay. So now this time I'm going to let t naught equal to 0. So t naught is your basically starting time. We integrate from t naught to t. T is the current time. So let's say if we make a simpler case, let the t naught equal to t. So then this solution here will become e to the power ft x naught 0 to t e to the power of t minus tau g u tau, okay, d tau. All right. So that simplified a little bit. Okay. Yeah. Okay, this still really haven't answered the question yet, what e to the power ft is. Okay, yeah. Now, I'm gonna keep this one at here. Keep this one at here. Okay. I'm gonna shift my attention back to this state equation. The state equation is x of t. Here's derivative equal to f x of t times g u of t. Yeah. This is the original state equation for the continuous system. So, and now I'm going to take Laplace transform of both sides of this equation. Okay, so basically we take Laplace transform, okay, of both sides of this equation. So if you take a Laplace both sides of this equation, basically you put the Laplace sign, it's not a Z sign, Laplace sign on both sides here. Okay, so this is our taking Laplace transform, right? For the left side here, this is a derivative. Okay, this is a derivative term, and if you recall, when you take Laplace of derivative term, so the left side here becomes s times capital, make it a capital now, so this has become s, and then you have to take into the initial condition into consideration. So whenever you have a derivative term, you take a Laplace transform. So that's what this basically looks like. Okay, and this s here basically is a derivative, right? You know, take a derivative of this, and you get x of dot. But you have to take the initial condition here. And the other side is easy. So f at here, so capital X s at here plus g and u of s. Okay, so that's the results of taking a Laplace transform of this state equation. And then I will simplify this a little bit. Basically, move this term to the same side as this term here, because I have a common factors here, right? X of s. So take out this common factor x of s. Now this is basically where this is s times this, and this f here, it's a matrix, right? This is a matrix, n by n matrix set here. So when you take the common factor out, you cannot use a scalar s minus a matrix, right? So what happens is you have to use s multiplied by a unit matrix I at here, which is n by n, and then minus f at here. Then I'll move this x of 0 to the same side over here. So that's the manipulation from this step. Okay. So far so good? Okay. Okay. So then I will divide both sides by this term. Okay, so divide this term to the right here. But this is a matrix, so when you divide a matrix, it really means what? You're taking the inverse, right? This is basically the inverse of that matrix. And then multiply by x of 0 plus si minus f negative times g and u of s. Okay. That's the results of this one. So essentially what I just did is I have written down the solution in a time domain, right? The solution in the time domain. And then I have written down the expression for x of s. Is that good? Right? So this is basically the two things we just finished. Okay. So what's the connection between these two things? If you just only look at the left side here, if you only look at the left side here, this is x of t, and this x of s is basically, if you take an inverse Laplace transform, you basically get back this, right? Yeah. So that's basically the connection here. And then on the right side here, if you compare term by term, you see this first term here, this is e to the power of t times x of naught. And this is a something times x of naught. That makes sense? Right? So basically what you do know is x of t is the inverse Laplace of this capital X of s. Okay? Yeah, that's your x of t. So if you compare these two terms, just the first term here, see the first term has the same x of naught. So which basically means what? If you take the inverse Laplace transform of this coefficient, that should give me what? Give me the e to the power ft, right? Yeah. So this is the results I'm looking for. So e to the power of f small t equal to the inverse Laplace transform of that expression. Okay. Yeah. And this is basically will lead us to the objective here. Remember, the objective is what's e to the power of f capital T, right? This is the objective. Okay. So the idea is, if you can get e to the power of f small t, how do I get e to the power f capital T? By doing, but I just what? Exactly, right? Just change the small t to capital T, and then I get that e to the power f t, right? Yeah. So this is why the step at here, we do this first. Okay. After finish this, then we replace that small t with capital T. There we go, right? We got that matrix A. Okay. So I think we're ready. Let's take a look at example here. Okay. Now in MATLAB, so we typically call this function here, call it phi at here. So we call this function phi here, and now actually, if you remember, this e to the power f t, when you're learning the modern controller, this is basically, if you recall that, what do they call that? It's called the transition matrix, right? And we're going to look at also the transition matrix for discrete system. But this is the transition matrix for continuous state space equation system. In MATLAB, you have a command that you can use, very handy. First, you have to declare a symbolic variable t, okay? And then you can use this command, which is called expm. So expm, just substitute this f times the small t into the function expm, and that'll return, basically, this will return this e to the power of ft value. Okay, yeah. And this e to the power of ft essentially is another matrix. Okay, it's another n by n matrix set here. Okay. But I want you to be able to calculate this using this formula by hand. Not for very sophisticated matrix, maximum 2 by 2, that should be enough. Okay, yeah. So let's take a look at an example at here. Okay? Yeah. Now in this example, I'm going to actually start from the very beginning. Suppose that you're given is a Laplace transform. So here's a Laplace transfer function for a certain system, and typically this is a motor, DC motor system. You have an inertia as a second order, okay, and then for position, describing the input voltage and then output position. Now we're going to design a digital controller to control this system. Okay, so here's your system. We're going to design a digital controller for this system. Then what we wanted to do is we want to discretize the system first into a discrete system, and then we'll design our digital controller completely based on that digital discrete system. Okay, so we're going to let's say assuming we're going to use a sampling time t equal to 1 for discretizing this continuous system in here, right? Okay, so this is a typical discretization problem in here. For this problem here, you see, what we need to do from here is let's derive the continuous state space model first, right? See, in the previous derivation, I basically assume I already have the continuous state space model, right? So in this here, I'm going to derive the state model. So what do we do is first from the transfer function in here, write down the differential equation. Okay, not difference equation. Write down the differential equation based on this transfer function. So here is your input, here's your output at here, right? Yeah. So what will be the differential equation in representing this system? It's very simple. Multiply the y with this one here, right? So you get y of s times s squared plus y of s 2s times this, then equal to u of s. Okay, so simplify everything, put it into one side as y, the other side is u. Okay. And bearing in mind the s is basically a derivative. The s squared is essentially second order derivative. So I can write it, this is y double dot t, and here is 2 y dot, right? And here is just the input u at here. Okay, so that's your differential equation in time. It is in time domain, of course, for the same system. And then from here, I will pick the states, okay, to write down the continuous states model. You can resort to your modern control, basically, okay, I can draw, actually you can draw, like what we learned in discrete, I can draw a simulation diagram, okay, and then pick state from the simulation diagram. But typically for this kind of second order system, okay, this is essentially in the same format as a mass spring damper system. Right, this is the same format as a mass spring damper system. Okay, or in electrical, you probably have a RLC circuit second order system. Okay, yeah. Then for this kind of system, what we can typically do is we pick our states purposely, not randomly picking up states. So we can pick our states, for example, let's picking state. So we pick our x1 of t, okay, equal to y of t, okay, y of t here. So the y of t here physically probably represent as the position, right? Y because it's output, right? So it represents probably the position information, okay? And then we can pick our second state to be the y dot, and y position derivative give us velocity, right? So you pick what we picked here is our two physical states. One is position, the other is the velocity. And the reason that we're doing this is because in the typical system, especially like the project, the experiment, you have sensors to measure the position. You also have the sensor to measure the velocity, right? Yeah. So we can make use of that as available, basically, measurements. Okay. So once we pick the states like this now, and then we can write down the continuous state space model. So as you can see, first of all, x1 dot, right? If x1 dot, that if you look at x1 dot, that basically equal to y dot, and according to our selection of state, and that's basically x2 of t. Okay, yeah. And then x2 dot, okay, x2 dot, which is y double dot, right? At y double dot. And y double dot, you go back to the original differential equation. Go back to the original differential equation. Look at this one here. What does y double dot equal? What is it equal to? Equal to what? Negative 2 y dot plus u of t. And then y dot equal to x2 of t again. So negative 2 x2 of t. Okay. Yeah. So this basically give us the state space equation, right, for the continuous system. And of course we will need the output here, but we can write this thing into matrix format now. So this is like x dot t, right, equal to this vector. Okay, it's a 2 by 1 vector here, and then you have a matrix set here, and multiply x1 of t, x2 of t, and plus this times u of t. Okay, so putting it into a nicely packed matrix. So looking at the equation, you can write down this is 0, 1, and this is what, 0, negative 2, negative 2, and then here 0, here's 1. Okay. So that's the continuous state space model. And don't be frightened that you say, oh, there's a 0 here. That's okay, right? Yeah, that's okay. Yeah. So then you can write down the output equation. So output here is single input, single output, and output is y, and y equal to x1 of t. So the basic means is 1, 0 times x1 of t here, x2 of t here. and there's no D term. Okay. So these two are the state space model for the continuous system. In terms of our symbol so far, so this one here is our F matrix, here is our G matrix, here is the C matrix, right? Yeah. Okay. So, and now we're going to discretize this continuous system using the results that we have just derived. Okay. And by the way, the way that we discretize the system, after discretization, right? Your originally is x of t. After discretization, it becomes x of k. Okay? Yeah, x of t to x of k. The physical meaning of the states will be retained. So basically, whatever the states over here, right? Whatever that represent, will also basically the same representation in this x of k. Okay? Yeah. Right, so let's go back here. Okay, now I'm ready to derive for the state space using the results now. Yeah. So I'm going to write down the discrete general equation first. Okay. This single input here, so which is basically just u of t, u of k. Okay, go back to our formula. Basically, remember the a equal to e to the power of ft, and b equal to integral 0 to this f lambda times g, and then d lambda. As we said, we don't calculate right away. We calculate e to the power of f small t, and that formula-wise is the inverse Laplace of Si minus the F matrix inverse. Okay. So this is basically the formula for e to the power ft, the transition matrix. Okay, so if you look at this one here now, so F, as we just derived, F is matrix 0, here 1, here negative 2. Okay, that's your F matrix. Okay. So I'm going to ready to substitute this F into this inverse Laplace. Okay, so S times I, right? S times I basically is S here, 0 here, 0 here, S at here, then minus F, and inverse. Okay. Yeah. Now, simplify this. So this one becomes S minus 0, 0 minus 1 is negative 1, 0 here, S minus 2, which has become S plus 2, inverse. Okay. Yeah. And you can certainly use any symbolic toolbox to help you calculate the inverse of the matrix, right? Especially if you have a higher order matrix. But for 2 by 2 matrix, and I would recommend that you try to remember the inverse for 2 by 2 matrix. Okay. So when you have a 2 by 2 matrix, its inverse is so 1 over its determinant, AD minus BC. Okay. And then the matrix here, this is D, A, negative B, negative C. That's the inverse of a 2 by 2 matrix. So as you can see, you shift the position for A and D, and then put a negative sign before B and C. Right? Okay. Okay. So let's use that formula for this one here. So inverse Laplace. What's the inverse of this? First, let's calculate the determinant. So determinant is this times this minus negative 1 times 0. Well, which is good. So that just leaves me with the 1 over S times S plus 2 now. And then inside the bracket here, as we said, this is D. The D becomes S plus 2. And the A here is S. and then you put a negative sign in front of the b, so the negative 1 becomes 1, and this is 0, right? Okay, that's the inverse of this. Is that good? And now multiply this term into the bracket, okay, for each one of the term, right? Multiply with each one of the term, then we get, okay, so this times that is 1 over s, right? And that times that is 1 over s plus 2, and 0, and that times 1 over s plus 2. Okay, there, right? That's the results of this inside the bracket. And now time to take inverse Laplace for individual terms of this 2 by 2 matrix. Okay, the only one, probably this one is not so obvious, because the first one, 1 over s, is inverse Laplace. If you look at the table, we have it, which is basically the unit step function, right? And this 1 over s plus 2 will give us exponential function, basically. Okay, and then for this one here, I think the table probably also has something like this, but if you're not too sure, you can always do a partial fraction expansion for this term at here. So you're going to end up with basically this partial fraction expansion. Okay, then the inverse Laplace transform here, is still very simple, right? Yeah. Okay, so then we get the results now. So I'm going to write it down. So this is, remember, this is e to the power f of t, right? Okay. First one here, this is the unit step input, unit step signal. So typically we use u of t to represent the unit step signal, right? But if you look at the symbol, the usage of symbol, and then often in time also u of t represented the control input, right? So just I'm writing a symbol here. Just be careful that what this really means at it here. Okay, this is not a control input. This just means it's a unit step input at it here. Okay. Okay, and then for this term in here, you have a 1/2 unit step input at it here. Okay. Then 1 minus 1/2. This is e to the power negative 2t. So technically, everything, this is one-sided Laplace transform. So this whole thing should multiply by u of t. Okay. Yeah. To make it maybe simpler, you could consider this just 1 here, right? This just 1 here, and it's just 1 in here. Okay. Yeah. Because we're only talking about t greater than 0 values, right? Yeah. Okay, so then this is 0 here, and then this is 1, and then I have this e to the power of negative 2t, and then times u of t. Okay. See, that's it. That's basically your e to the power of ft, right? E to the power of ft. Then my discretized system, the A matrix, is to replace the small t with capital T. Okay. So here, you don't have to replace the small t with capital T for the unit step. But that's basically is 1, right? So just take it a 1 here. And here is 1/2 minus 1/2 e to the power of negative 2. That replaces the small t with a capital T. Okay. Yeah. And this is 0 here. This is 0. This is e to the power of negative 2t. Right. That's basically your A matrix at here. Okay. Yeah. Is that good? So my expectation is for simple 2 by 2 matrix, okay, you should be able to go through these steps to obtain this A at here. Okay. Yeah. And B matrix. Okay. If you look at that formula. Okay, that's a B matrix. So let's try this one here. We do the same thing. So you see here, you have a e to the power of f times lambda, right? F times lambda. So what do we do? Basically, instead of replacing the small t with capital T, we replace the small t with lambda here now, right? So essentially, here is the matrix here, but you're replacing this t with lambda here, so 0. Then times the G matrix. G matrix is 0, 1, and then d lambda. Okay. So that's your B matrix. Okay, so this one needs a little bit careful calculation integrals here because it involves integral. Okay. When you do this integral, you could integrate basically. This is a constant here. You could take this constant out of the integral, right? But I would recommend that you multiply the two matrices together first, because that's 2 by 2. Once you multiply this, it becomes a 2 by 1, right? And that'll simplify. Basically, now you only deal with the integral of 2 terms now. Okay. Yeah. So let's multiply this together. Then what do we get? We get 1/2 out of here minus 1/2, and then here's E, and then d lambda. Okay. All right. So then all you're left with just integral for this term and this term now, right? Yeah. And I think that's fairly fundamental. But according to my experience, and often in time, some students still having trouble with reading variables, the exponential type of function. So if you're having trouble with that, just do some reviews. Okay, you should be okay. And we end up with 1/2 t plus okay. So here's basically what you get if you integrate each one of the terms. Okay. And this is the B matrix. Good? Yeah. Okay. Yeah. You can substitute the t, which is 1 and here, and then you can calculate the values of each one of these, right? Yeah. You can also try MATLAB to help you. Basically, if you try this, first give the continuous system matrix F and a G. Okay. Here are the continuous system F and a G. Then you can use this C to D command, plug in F, plug in the G, and then give the sampling time TS. You can let it return A and B. So that should give you the same calculation, same results here. Okay. Okay, so that's basically a very typical example, starting from a continuous Laplace transfer function, and how do we, for a system, how do we discretize that to give us the A and the B, which is the matrix for system matrices for the discrete state space model. Okay, yeah. So be familiar with this. This is, I guarantee you're going to have a question in the midterm. Yes. Where? Here? Should there be a 2? Oh yeah, should it be a 2? So just a second here, let me see. Yeah, you're right. There should be the 1/2 here, isn't it, right? Yeah, I think so. Huh? No t should be the 2. Just looking. Oh yeah, you're right. So 0 t time t sub t is 1. Yeah, you're right. Yes. Good point. Good catch. You see, I made the mistake. Yeah. So this is good, right? Yeah, because this is 2 here, right? Yeah. There we go. Yeah. Okay. Perfect. Okay, so there's one little loose end here for this section. Then we're pretty much done with this section here. Okay. Yeah. So the last concept here is, So considering now you got your discrete, basically state space model now, and the question basically here is, can I going backward to obtain the pulse transfer function from a given discrete state space model? Okay. So it's basically like a backward. You know, in the previous lecture, what we did is by presenting a pulse transfer function, right, g of z, for example, and then we put it into the simulation diagram appropriately, and then we derive a discrete space model, right? Yeah. So here, what we can try to do, let's say you have a discrete space model. So basically, you have a discrete model like this. Okay, like this. Can we go from here and then get our pulse transfer function? Okay, that's the point. I'll use single input, single output to illustrate this idea here. Okay, so here's a discrete space model, and what we want is a pulse transfer function, PTF. And PTF describes the relationship between output and input. So basically, what does this equal to? So here's your output, here's your input, right? Yeah. And we're looking forward to an expression for the pulse transfer function. Okay. So what we do is, it's very simple. Based on the given state space model, we're going to take Z transform, okay, of both sides of this equation first. Okay. And we're going to actually later we're going to take Z transform also for this one here. Yeah, so that's what we're going to do. We're going to try to take Z transform. So let's take a look at the first one. Taking Z transform of this one here. So what would that give us? Okay. So from here, this is x k plus 1, okay? And if you look at the table here, you have a property when you have a discrete function k plus 1, and then you get z, x of z, and then minus z times the initial condition, okay? Initial condition. And then here is a times x of z plus b times u of z. And then the next term in here is y of z equal to c x of z plus d and u of z. Okay. Good. Yeah. And when you derive pulse transfer function, okay, or even in the continuous system, when you derive the Laplace, the impulse response, the Laplace transfer function, and one of the assumption is we will have to assume the initial condition to be 0. Okay, so we're going to have to assume initial condition to be 0 in order to get our impulse, basically transfer function. Okay, so assuming this one to be 0 now, so you'll be able to get rid of this term. Okay, yeah. Then based on the first equation and here, right, and grouping the similar terms, so you have z x of z, you have a x of z, so move this one to the same side. You have a similar situation like the previous one here, because this is a scalar z, and this is a matrix A. So basically, you take out the common factor, and then you have a zi minus the A over here, right? Yeah, z times the unity matrix first, and then minus A. And then equal to b u of z. And then divide this zi minus a to the other side, obtaining the expression for x of z. So we get zi minus a inverse times b u of z. Okay? Yeah. Here's your xz. Once you get your x of z, then replace that x of z, replace this one here with, okay, inside this output function y here. and that gives us y of z equal to c times zi minus a inverse b u of z, and then plus d u of z. Okay. All right, almost there. So now on the right side, both have a common factor u of z. So now you have your pulse transfer function, which is what? C times this, and then plus the d. And this is your pulse transfer function, basically. This is your PTF, okay, based on the discrete state space model. Okay, yeah. Is that good? Yeah. So I want you to try yourself. Basically, you see the example that we had here. What did we start with? We started with the Laplace transfer function at here, right? Yeah. And then end up with a discrete system, which is zero-order whole equivalent. Discrete system A equal to this, okay, and then B equal to this, right? Yeah. And what will be the C? C will not change. C will still be this 1, 0 at here, okay? Yeah. And D is just basically 0 at here, right? Yeah. So if you apply the formula, basically if you apply the formula like this one here, CID0, if you apply this, you're supposed to get h of z, basically equal to something, right? Yeah. Okay. And I want you to try this. Basically, try what h of z equal to, right, from the example. Okay. Yeah. And at the same time, and also try this. This h of z should be the same from the original system. Right? This is your plant at here, right? This is the plant. And what are we deriving? We're deriving what? The zero-order whole equivalent, right? Zero-order whole equivalent. So you have a basically assuming there's a zero-order whole in front of the plant at here, okay, and that discretizing this one, right? Discretizing this one here, or getting let's see, I'll call it h of z, but it's okay. Yeah. All right, getting this h of z. So whatever you get from here should be the same as what you get from here, right? Should be the same as this, because they're all zero-order whole equivalent. This is discretization. This is pulse transfer function, right? This is essentially 1 minus z to the power of -1, and z 1 over s squared and s plus 2. Okay? Yeah. Okay? Yeah. So you can try from results from here, results from here. These two should be exactly the same. Okay. Yeah. Okay. So that's basically the parts for discretizing a continuous state space model. Okay. Any questions? Okay. Good. All right, so let's continue from here. Now let's look at the new topic. It was to continue along the line, essentially the discrete state space model. Huh? Yeah. So the next topic is about the solution of a given discrete state space equation. Okay. A solution of this. So what's a solution? Essentially, what we're talking about here is. Here is your state equation. Okay, here's the state equation. It's a vector, containing a vector of states, x1 of k, x2 of k, right? Yeah. Like the example that we give here. I should actually emphasize one thing before we move on here. Coming back to this, okay? Coming back to this example here. So you see, we picked two states. One is position, right? And the other is velocity. Okay, the velocity. And then we discretize. After discretization, we got x of k here, right? So you should actually bear in mind this x of k containing x1 of k and x2 of k, right? x1 of k is a representation of what? Position. This two, x2 is the velocity. So it retains, they retain the previous defined state variables, right, in the continuous domain. Okay, yeah. So that's actually the nice part, that you manually designate what type of state you use for the system. That's one of the things that different from a method command. Sometimes when you use a pure command, it's a mathematical approach. The states that you use is not necessarily the states that you want, right? So sometimes it's actually more beneficial to start manually, like this, picking the states, position, and velocity, and then you continue with the assistance of the software for you to solve for discretization or for future calculations. Okay, yeah. Instead of everything is completely using the software. Right? Okay, so suppose now we have this system now. So solution, basically what we're saying is, what does x of k equal to? Right? That's the solution we're talking about here. This is the difference equation. It's the counterpart of the differential equation. Differential equation, you get x of t, right? Solution for x of t. Here you get a solution for x of x of k. So how do we solve this one here, right? So we can solve this one by iterative approach. And for example, at the k equal to 0, what do we have? We have what? X of 1 equal to a times x of 0 plus u1, u of 0, right? Yeah, that's the first. It's like a programming. You start a loop, and the input to the loop is initial value is x of 0 and u of 0 here, right? Yeah, and then after iteration of the loop, you get your x1 basically. Okay, yeah, and then you can continue it here. Then at the k equal to 1, the second iteration of the loop, that gives us a times x of 1 plus b times u of 1, right? Okay. But I already have x of 1, which is from the previous step. So you store somewhere, right? And we can substitute this x of 1 from previous step. So that gives us a times a x of 0 plus b u of 0 plus b u of 1. Okay, yeah. And then simplify this a little bit here. You get a squared times x of 0 plus ab u of 0 and then plus b u of 1. Okay. That's the second iteration here, right? So you can imagine, keep going, right? So k equal to 2, and keep going up to maybe, let's say, until this k equal to k steps now, right? Yeah. So at x of k at here, that's the solution we're looking for, right? A solution here. So what does that equal to now? See, with a comparison, this is x of 2, this is a to the power 2, x of 0. So at x of k, or the k steps, this one got to be what? Got to be a to the power of k, x of 0 here, right? Yeah. Yeah.
Would it be k? So when k is equal to big K, would it be x of k minus 1 or k plus 1?
Yeah, you're right. Yeah. Just a second here. When k, yes, this is. I guess I should see this is at. Yeah, you're right. Just a second. What's going on here? X of. Yeah, sure, you're right. Yeah, this should be at k equal to k minus 1 here, right? Yeah, k minus 1 steps. Okay. Yeah. So basically, at the k minus 1 steps, we got our expression for x of k. Yeah, excellent. Okay, and then you have a whole bunch of term associated with the control u of 0, u of 1 at here, right? Yeah. So as you can imagine, basically there will be a times b times this, or there'll be a squared times b times this. So all of this term in here. So you can put this term together, but that's actually not what we're looking for. But you can put these things in a very brief, very short, brief description using the summation sign at here. So this become a times k minus 1 minus j, and then times b u of j here. Okay. So if you want to try, let's say if you let the k equal to k minus 1 steps, basically let's say when you let the k equal to 2, right? If you let the k equal to 2 here, so this will become 2 minus 1. This is 1 to 1. So you should get, actually, what's going on here? Should I get the same thing? Oh, this one's 0, sorry. 0, yeah. Slight mistake. So if you put k, let's say if you let the k equal to 2, right? Let the k equal to 2. And that this term here should give me back these two terms, right? These two terms here. So let's try it here. So that's give me a to the j from 0 to 1. So when j equal to 0, and this is a times, when j equal to 0, 0, and then you pick the first term, which is 0. So anyway, you can try yourself. So trust me, this is okay here. So but if you substitute k equal to 0 here, so that's j equal to 0 to 1. Okay, like that, right? Like that. Okay. So let's see. Let me try it here. When j equal to 0, so this is equal to 2, right? So 2 minus 1 minus 0. So yeah, so 2 minus 1 minus 0 times b, u of 0, right? Yeah. And then plus a to the power of 2 minus 1, and the next one minus 1, and then b u of 1. So that's the same as these two terms here, isn't it, right? Yeah. Okay. Yeah. So anyway, actually what we're really interested in here is the first term here. But overall, okay, so here, this one here, this is basically called the solution, right? This is the solution of that difference equation. Okay? Yeah. Just like the solution corresponding to that differential equation, right? You have x of t. Okay. Now from this solution at here, there's a very important observation, very important matrix at here, which is the matrix, which is this matrix. Okay. So you see this matrix, a to the power of k, is the coefficient for x of 0, right? Now, if you recall that for the continuous system, what was this solution again? The solution here is here. I have a better one. Where is it? No, let's look at this one here. So this x of t equal to this one times this, right? Remember that e to the power f of t is called transition matrix. Okay, so transition matrix essentially means you have initial condition x of 0, and how does that initial condition be transitioned into the current value or current state? It's completely based on what? Based on this a to the power of k, this coefficient here, right? Yeah. Especially, let's say if my input is always 0. If my input is always 0, then the second term is always 0, right? Then the system response will be completely depending on the initial condition, right? Or in other words, it completely depends on this a to the power of k at here. Okay? Yeah. So this matrix here, we're going to define this phi of k equal to 8 of k here, okay, is called state transition matrix. So this is a state transition. State transition is very important actually matrix at here. Because why? So let's go back to the time function at here, to the time here. Okay. Let's go back to this one. Suppose all of the control input is 0, so there's no second term here, right? There's only one term in here, only one term. Okay. And even to make it even a very simple case, consider it's not a matrix of multi-dimension, just a single scalar, so 1 by 1 matrix. So the F at here is just a 1 by 1 matrix. Is that okay? Right? Yeah. Now the question here, if you look at this one here, here's x of 0, here's x of t equal to this times that, right? Yeah. So let me ask a question. If I start with initial condition x of 0, right? Okay? Yeah, start with x of 0. And I want the responsive system. Forget about the u. There's no control inputs, right? So here's your input, output here is x of the state, x of t equal to this. And I want this one to go back to 0. Okay? Is that good? So here's you start with a 1 or 2 for something, right? But I want this response, right, to go back to 0. Okay? Not going somewhere else, to gradually go back to 0. Then what do I need in order for that to become true? I can't change this. This is given, right? If I want this one to go back to 0, what do I need for this term? Decay, right? Exactly. Decay meaning the f has to be negative. Very good, right? And negative actually basically means you have a pole in the right hand side of the S-plane. Okay? So coming back to this one here, right? Coming back to this. Here is a state transition matrix here, right? Here's the state transition. Let's still start with a very simple case. Okay? Suppose I have a scalar, so everything's scalar. So the A at here, it's not a matrix, it's just a scalar, 1 by 1 value, right? And I start from x of 0. And I want my state at here to gradually go back to 0. Then what do I need this A value to be? Smaller than? That's right, right? Because you need a 0 point something, right, to the power of k. As k goes to infinite, the 0 point something to the power of k will become 0. Okay? So that's actually basically, in the later we're gonna generalize to more, because I use a very simple scalar, right? Yeah. Now what if the A is not a scalar, is a matrix, so let's say a 2 by 2 or 3 by 3 matrix, whatever, right? Yeah. I want the same thing. Start with a set of vectors that's not 0, but I want my states all go back to 0, right? Yeah. So essentially you want this A to the power of k, as the k goes to infinite, you want it to gradually to become 0, right? In order for that to be realized, and the conclusion here will tell you, the A at here, its eigenvalue has to be within the unit circle. Okay? Yeah. So that's actually the idea why we want to study this state transition matrix at here, right? Yeah. So this A to the power k is a state transition matrix. Okay. So then the natural question at here basically is, so how to calculate this A to the power of k, which is a state transition matrix. Okay. And then you might think, well, that's easy, let's just keep doing matrix multiplication, right? If I ask you, let's calculate this A to the power k when k equal to 100. So what do? Well, if you're a math level, it's fine. You can calculate this 100 times, right? And then you multiply the matrix 100 times, you get the results. Okay, but that's not probably the most smart way to do it. What we really want here is, I want to obtain an analytical expression for this a to the power of k. Okay, yeah. Let's look at the first method at here. Okay, let's look at the first method. I'll give you two different approach. Okay? So for the first method here, what we're going to have to do, we're going to have to start with our original state equation. So here is the original state equation right here. Okay? And I'm going to assume my input to be 0. Okay? So I assume the input to be a 0 here. Then we will take the Z transform of both sides of this equation. Okay? So because this is 0, so that term will be gone. Right? So I'm going to take a Z transform of both sides right here. Z transform for the left side is Z times capital X of Z, then plus the initial minus Z times initial condition, and then here is A times X of Z. Okay, A times X Z. Okay, so move this term to the left and move this term to the right, and we get X of Z, Zi minus A equal to Z X of 0. Good. Then I can solve for X of Z, which is, okay, so solving for X of Z, which is Z times Zi minus A inverse X of 0. That's the solution for X of Z, okay, when assuming the control input is 0. Now why I'm doing this is because if you look at the solution, right, from the previous steps here, here's a solution for X of k, a to the power k X of 0, right? If u is 0, then this whole term is gone, right? And then here is the solution for X of Z, which is this, when u is 0. So both of them has the same initial condition, right? And then this X of Z is basically the inverse of inverse Z transform, right? Give you the X of k. That makes sense, right? So that basically means the state transition a to the power of k is the inverse Z transform for that expression over there. Okay, so that's your state transition matrix. Okay, so this is the analytical way you can calculate what a to the power of k is. Right? Yeah. Good. I'll show you an example to see how we can calculate this one here. Right? Yeah. So this is A matrix 0, 1, negative 2, negative 3, okay, and we wanted to calculate a to the power of k. Okay. I'm going to use this formula right here. Okay, use this formula to calculate this a to the power of k. All right, so let's plug in this formula here, Z. So first, let's look at just what's inside this bracket here. So let's just look at this term here. Okay, the inverse here. So Z times, so Zi minus A, here's A at here, and Zi is Z times the unity matrix. So that gives me Z here, Z negative 1 here, 2 here, Z plus 3 at here, then inverse. Is that good? Yeah. So now I want you to use the formula for the 2 by 2 matrix, the inverse for the inverse of 2 by 2 matrix, to calculate this one here. Okay. So you have the formula written previously there, what should I get? That should give me determinant is z times z plus three minus, which is 2. Anything? Yeah. Okay. And then here inside here, this is z plus 3 at here. This is going to be z at here, and that's going to be 1, negative 2. Okay. And now time to clean up a little bit at here, especially for the determinant, right? This determinant here. What's this determinant? The determinant is z square plus 3z plus 2z, right? So that's plus 2. And this is equal to, yeah, right? Yeah. Actually, I was helping my kids last night, you know. It's a factorization, grade 9 stuff. So I'll move this one over here. There's a z here, and then multiply everything into the bracket. Okay. Somewhere you can make some simplification, but not everywhere. So this one here, you get z times z plus 3 divided by z plus 2, z plus 1. And here you get z over z plus 2, z plus 1. And then here's negative 2 over z times z, z plus 2, z plus 1. Here you get a z times z, so z squared over z plus 2, z plus 1. Okay. Good. So this is basically what's inside this bracket here, right? And now we're trying to do is take the inverse z transform for each one of this, right? For each one of this. Okay? It's actually not too bad, actually. So the inverse, taking inverse z transform of this, assignment number 1. So what do you do with each one of these? You have to divide each one of these one with a z first, right? And then you will take the partial fraction expansion for each one of these. Okay? Yeah. Is that good? Yeah. So unfortunately, actually these two are well. Unfortunately, none of them are the same actually. So you're gonna end up with completely 4 different partial fraction expansions. But with the careful calculation, so you are gonna get there. So that's your a to the power of k. Good? Yeah. So yeah.
Super unstable.
Super unstable, that's right. Yeah, that's just for example. Yeah. So this one here, you can see the eigenvalue in this case, which is one is at -1, and the other one to -2, right? And they're not within the one of this on the unit circle, but the other one's outside unit circle. So yeah. So it's well, yeah, but back and forth. But as k go to infinite, this goes to infinite, right? Yeah. So this a to the power k ultimately becomes infinite values for each element. Yeah. Okay, so that's the example for this first method of how to get a of k, right? Yeah. The second method here, so I'll just start with the second method here. Okay. Yeah. The second method here is a very mathematical approach. It's basically using linear algebra technique, which actually will bring us to our next topic. So linear algebra, I'll show you one phenomenon first, okay, and then we'll see where that leads us to. So here's an observation. Okay. So observation is this. What is the power of this matrix to the power? What is the case power of this matrix set here, right? Yes. You can just do this, right? Yeah, very good. So that's very simple, right? You know that basically means, you know, when you have a diagonal matrix, its power to the power k, it's just simply the diagonal matrix element to the power of k. Okay, yeah. But this observation, right, doesn't apply to a generic matrix. But this is not zero here, then you can have this one here, right? Yeah. So now this brings us to the question here. Let's say, given a matrix A at here, right? Given a matrix A at here, can we somehow, right, transform this A matrix to a matrix of a diagonal format, and then we can make use of this result set here, basically, right? Yeah. So we do have essentially the next topic here called similarity transformation. Is you can, if you look at this, if you look at the one I'm writing here, this -1, this -2, that's basically the poles or the eigenvalues of the original matrix, right? Yeah. So if I call this is, let's say, if I call this is matrix AW, okay? So basically AW here is a diagonal matrix whose elements are the eigenvalues from original A matrix. Is that okay?
No, does it matter which one the first eigenvalue is?
It doesn't matter.
Like, so it can be -2 and -1 instead of -1 and -2.
No, it doesn't matter for AW, but what it does matter is because when you do the similarity, which is what I'm going to write here, we have this kind of similarity transformation. So you write down the AW, right, with the diagonal elements as the eigenvalues. Okay, yeah. But of course, this is different from the original A matrix, right? So how do I get it back? Then I have to use another matrix, capital P at here, to get back to this original matrix A here. So this writing in here is called basically similarity transformation, right? As you were saying, if I write AW here is -2, -1, then this P matrix will be different, right? Yeah. Okay. So of course this is a question mark. So what is that capital P, right? So we're going to have to look at that. But suppose that you are able to write the A into this format here, right? So now let's observe this. Okay, so this AW, right, is equal to this, for example. So now let's observe the calculation of A to the power of K. So A to the power of K is equal to P times AW P inverse to the power of K. Okay, yeah. Okay, this seems to be not so simple yet. So now here's that the clumsy method here. So I'm going to multiply basically this whole thing, k times. Let's take a look at what can we see here, right? So I'm going to basically write these things. Oops. Write these things k times at here. There you go. Okay, I think you probably start to observe something here. So take a look at this. Let's write another one here. Right? If you look at the adjacent two terms here, P inverse times P equal to what? Is I, right? And this times this equal to another I. So if you follow through the chain, all of this P inverse P, P inverse P, they all actually disappeared, isn't it? Right? They all disappeared. So basically, you end up with what? Just the front P and the last P inverse, right? And in between, it's AW, 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 AW multiplied together by k times. Okay? And we just said AW to the power k is so easy to calculate, right? And P is something that we're going to find it out next lecture. So once we found the P inverse, and this one, you get to a to the power k. Okay? Yeah. So we'll look at basically the next topic, similarity transformation, in the next lecture. Okay.